Okay, so this is today's outline. There will be two parts because this is the first lesson where we're talking about the very fundamental about the semiconductor laser. The first part will be the historic perspective. There will be how does this term be invented and how does it develop into the present stage. And the second is talking about the semiconductor material and how we prepare that. So we're not going to dig into the physics. So we're going to talk about something relatively fundamental first. So what is laser? So laser, it is not even a word 100 years ago. It's an abbreviation like ASAP or LLL and GG, something like that. This is an abbreviation, but it is used so common. So this abbreviation eventually registered into a final word that everybody uses. For example, now actually you can register and check with the British dictionary. There's actually a word for ASAP. Yeah, you can look at find ASAP in the dictionary. So that's the same scenario of the laser. So laser is in the beginning that stands for light amplification by stimulated emission of radiation. Okay, probably you know every word of each word, but you don't know what happened when you put it together. Anyway, if you see all the first letters LASER, so that's the word laser comes from, and this term is firstly used by people called Gordon Good, and Gordon Good has been fighting for his right. Say that I invent this term for a patent war. That long last about 30 years, so that will be another story. So anyway, so if you ask, if you have a time machine and find Einstein, talk about how do you come up with the idea of the laser? He might answer, what is laser? I never heard of this word. Yeah, because this term is invented in 1960s. But before the laser terms, there's the so fundamental physics field before that. So the first one that comes to the most relevant, that's the first lesson you will learn about the modern physics is black body radiation. In 1990s, Max Planck is a scientist and he received some money from the General Electric to study about how to make an incandescent bulb, 还是灯 brighter. So his research is trying to find to analyze the spectrum of a heating material, or we call it black body radiation. And then he finds that if you assume the light with infinitesimal energy, that will never get the right spectrum. So at the beginning, he made a very bold assumption that like the energy of light has a minimal value of infinity. He called quantum, and later he eventually introduced the idea of the quantum mechanics. But at the beginning, it doesn't have this particular reason. He just finds if I can assume the light to be the positive integer of something, then he can fit the spectrum right. So in the beginning, it is just something like a 技巧. Yeah, because if I can do that, then I can do the right data. But he didn't really give how does this come. So, but this energy increment has eventually evolved into the next concept called photon, and that's what Einstein do. So Einstein is that everybody know, but and the probably his most famous theory is the general relativity. But what makes him a Nobel Prize laureate is because he proposed the idea called the photon. He said that there is a photoelectric effect, 光电效应. And he also proposed a mechanism of stimulated emission for something called AB coefficient method. And we're also going to teach that in the lecture 4. Yeah, he won his Nobel Prize because he said that the energy has a particle behavior, and this particle we call it photon. And its fundamental increment is proportional to its frequency. So E is equal to H mu. Yeah. And this kind of stimulated emission is just a paperwork. He just wrote the writing on paper. He didn't have any evidence. But later, probably like almost 10 years, another very famous people called Paul Dirac conducted an experiment to confirm this data. And the Paul Dirac is also the Dirac notation. The Dirac you know from the quantum mechanics. And he also earned the Nobel Prize in 1933. Okay, so later on this idea stopped a little while because we don't have a good platform to prove this theory until 1954. Dr. Towns and Dr. Shallow they are inspired by Einstein theory and designed a very simple cavity, a tube with two mirrors, and they injected ammonia within that and do glow discharge. So the ammonia is excited. Then they found a stimulated emission in the microwave region. So they invented the term maser because the M stands for microwave. The wavelength is around 10 micron. Yeah, so they become really famous, and they also earned the Nobel Prize in 1964. Yeah, no doubt, because they are the first one really proved a concept of the stimulated emission into something like device. And Gordon Good is their student. He think if we can make it in the wavelengths of microwave, it can be made in the arbitrary wavelengths or wavelengths. So he just changed the idea with M, microwave, into light. So it becomes a laser. But he also didn't make a laser. He just write it in the notebook. So writing things in notebook is very important. That will make you even like eventually evidence about your idea. Yeah. And this is the famous notebook. He just designed a very simple paper prototype. This is all the figure you got. So I have a mirror 1 and a mirror 2, and with the lens L, so the light can go back and forth and eventually become a laser. Yeah, just an idea. Doesn't make any device. Then, who is the real people making the first solid state fixed laser? It is a scientist in the HRM research lab. It is the lab in California, near the Malibu, very beautiful view. Anyway, by the time the maser, the gamma is ammonia, is gas. And the people are asking, is it possible to make, because you don't want the bulk of a tank of ammonia with you. So if you can make the gamma into a solid state, that would be much more applicable for real applications. But people at the beginning don't think this is gonna work, because the reason I will talk about laser. But the scientist Theodore Neyman, he just proved that it is possible, and then he built the first ruby laser with L203 as the gamma. And this is the first working solid state laser. But because he eventually found it, he didn't win the Nobel Prize. But the solid state laser isn't still good enough for application, because for solid state laser you need another light source to pump the rod, the ruby rod. So you are still generating light with light. This is not ideal enough. The best scenario is we can generate light with electricity. Yeah, because electricity we can store it, and we have a big power plant and build it anyway. So the energy conversion efficiency will much better, and the size surely will become even smaller. So people are asking, is it possible to make an electrically pumped laser? And that doesn't come too late. It's only two years later. By the time Nick Young Jr. By the time he's still a scientist in general electronics, also general electronics, and later he becomes a professor in the UIUC. Anyway, While he is a consulting scientist at the General Electronics Lab, he applied the same concept with a very prototype cavity, just with a decent design with the cavity and the electrical injection. Adding up, we have a pretty good material with GASP. So he demonstrated that we can make a light-emitting diode into a laser. So this is become the first electrically driven laser in the world. But pitifully, many people think that he should earn the Nobel Prize. But because by the time finally the winner is the people who invented blue LED. So some people is very unhappy about that. But anyway, but he's still a very great scientist. I think he didn't need such honor to prove himself. So the most common laser nowadays, even till now, is the heterostructure laser. Double-heterostructure laser is the primitive form, the early form. That means you have a semiconductor with different band gap. So at the beginning, if you have only a simple PN junction, it is very difficult to make the carrier to confine in a very small region. However, if we design something like that with a PIN, or this PIN is probably not the most common one, it's usually PIN. And the center part has a smaller band gap. So while the electron injected and the hole injected from both sides, the carrier density will be much higher than this homo junction. And because you can combine your carrier in the middle, so the carrier density is high, so you can eventually get a positive gain. Yeah, we were circulating this idea again and again and again. So eventually, because we have this mechanism, we have a carrier concentration with like a heterostructure. Because we have one heterostructure and two heterostructures, so they call it double heterostructure, DH laser. So we have a combined design for carriers. Fortunately, for those material with a low band gap, usually has a high refractive index. So it also works as a waveguide. So you have a confinement for electron, confinement for light. So electron and the light are put in the same ring and interacting with other strongly. So this is the fundamental of the laser. And the pioneers who working on that is Herbert Wimmer and Doris Arnold. Along with a third Jules Kirby, they win the Nobel Prize of 2000 year because they build the fundamental of the fast internet. Yeah. Why do we have a so fast internet? One is the VSLI 机体电路, and the second is the very fast optical communication from city to city. And both those technology are all built based on double heterostructure in semiconductors. So they also regarded the high fun in physics, although relatively late. Okay, so actually there's so many milestones in the development of laser. Even the Professor Nakamura is also my physics doctor professor. He also won a Nobel Prize physics for inventing of the blue LED, but he doesn't own that because he achieved a blue laser. But he also is the one achieving blue laser. So anyway, so semiconductor laser diode is a very long life topic and still living. Yeah, because some research field probably is very hot 50 years ago, but now nobody can study that because it's too mature. However, semiconductor laser diode, because it involves so many research fields, and there's always new breakthrough from every aspect. Sometimes because you build a new material, and this new material demonstrates laser, then you make a breakthrough. Or you have a common material like a gallium arsenide. Then you use gallium arsenide to construct a new cavity. For example, you make a photonic crystal laser. Okay, that's also a breakthrough. So because the achievement of semiconductor laser diode involves so many aspects of the physics. It could be from fundamental physics, material science, electrical control, and many so on. And there's also many applications due to its superior performance. So it's still a living research field up to now. So okay, so about the simple history of the semiconductor laser diode. But what makes a semiconductor laser diode? So there's definitely some forming element. Like for human, you have a head, you have two hands, you have two legs. But if you don't have one leg, one hand, are you still human? Okay, yes, you're still human. But if you don't have a head, are you still human? Probably not. I think you're just a dead body. Okay, so there will be some essentials about semiconductor laser diode. What is must included in the semiconductor laser diode? So the first is it must be pumped. A pumping method. It's usually optically pumped or electrically pumped. Optically pumped, that means you shine a very high intensity of light to make the material excited. The electric pump, that means you have the electrode and the inject carriers. Anyway, it's how you make the lasing. I make the material excited. So that's a pumping method. And the second one is usually you need a gate medium. That's about which material is providing the gate, or what is the gate. We will learn that later. You can imagine this is an engine to a car that makes the car moving. Yeah, this is the core, the gate medium, which makes the material work. And it could be so many things. It is proven in helium-neon, a gas, CO2, also a gas, so fiber, solid, and sometimes it could even be liquid if you want to do that, although it's not very convenient to achieve. So as long as something you have a high energy and a low energy, yeah, that sounds pretty broad. There's a lot of material has a high energy and low energy. It could be a gate medium. And the third, you have a good cavity. A good cavity, that means because the laser needs the light and the material to interact with each other very strongly. So if you light just go out to outside, they don't have a chance to interact with material. So usually you need to create a cavity intentionally to keep the light within a small area. So the light and the material keep interacting with each other. So this is the purpose of the cavity. And there are so many ways, people are still inventing new ways to make a cavity to keep the light and the material interact. It might be very peroxide. We will be focusing on this type of cavity first. And the rest of it probably you can try that. And there's also so many like plasmonic is also kind of cavity. Random laser is a cavity. It's a cavity, you don't know what a cavity is. But experimental says there's a cavity, so yeah, that also count. And like whisper grain or nanowire, that's all type of cavity. So if you can make some combination of these three ways, and nobody tried that, and that's a breakthrough. Yeah, because you demonstrated the first blah blah blah, and then dot 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 lasers, and usually you will get a very high rating about that. So let's go to the most common, the most simple material system. Let's assume this material only has two levels. One is called the low level. Low level is level 1. And high level just called the level 2. And the electron can be either in low level or high level. You don't have so many choices, low or high. Either one of them. Okay, so if the electron is initially at a high level, and it cannot stay long, sometime it will return to the low level. And the thing's energy, the total energy should be conserved. So where does the energy go is important. If the energy difference become heating, become the lattice vibration, something like that. Okay, you just generate nothing. The electron goes to the lower level and the energy is wasted. So this is not what we want. It is called non-radiative recombination. But if the electron from high level return to the low level, and the energy is returned as a photon, okay, you generate one photon, and the photon, the energy difference should be the difference of these two levels due to the conservation of energy. So you have a spontaneous emission because you don't know when this happen, and when this happens, when this emission happens, you don't know what the phase. You know it's energy, but you don't know the phase. It could be random, so it is spontaneous emission. That's the common mechanism of LED. Alright. So let's put it another way. If the electron is at a low level, if for no reason it didn't go up to high level arbitrarily, you must have some mechanism. If the energy comes from another photon with the same energy, then it will be absorbed. Okay, so the one electron is rising up from low energy to high energy, and this system lost one photon. This is called absorption. And the next one, this is the invention of Albert Einstein. He just like come up with in paper for some reason. Anyway, he said that if a photon comes in and your electron is over at a high level, at the beginning people think, oh, there's nothing gonna happen because you cannot excite it to an even higher level because there's no such level. But Einstein says, no. He said that this electron will trigger this photon will trigger the electron at a high level back to the lower level, and then the new photon comes out with the original one, with the same phase and the same magnitude. So this is called stimulated emission because this emission is stimulated by another photon. Okay, so if we like to write down the how fast things would happen, we usually write it down this way. The NP means we imagine that there's a cavity and there's an NP photon inside there. So if the light comes in, it will it's absorbed. So the dN over dP will be reducing. So dNP over dx will be minus P1 to N2 Pn1. That means if you have more NP, you will be absorbed faster. Yeah, because this even will be happen more likely. So dNP is a constant times the photon density times the carrier density. And we write it negative because we want this coefficient to be positive. Okay, so don't need to be clear. Similarly, if you make the stimulated emission, you have the same way to write down the equation. The downward transition will be faster if you have more coming photons or more electrons at high level. So it will be B21, a coefficient, because it's from 2 to 1. B21 times NP, the number of cavities, times the number of carrier at level 2. So we say the N2. So with some fundamental calculation, okay, you said that if the electron is in the low level, the light coming in will be decaying exponentially. In the other way, if you have the electron at a high level, and you have so many electrons at a high level, and the light comes in, the light will grow exponentially. Okay, so in this case, the electrons in the low level will make the light loss. So there's the parameter called loss. And for the stimulated emission, we'll give you a parameter called gain. Yeah, because that it describes how fast your light will be decaying or your light will be propagating. Then we consider there's so many electrons at the both level. Yeah, so the system is a little bit complicated. So you need to add it up two terms together, and you write it down. NP is NP0 exponential B21 N2 minus B12 N1 times X. So Einstein said that B12 is a B2. But that this statement is important. It says that these two mechanisms are pair interaction. The speed from A to B and B to A is the same. Yeah, so say that there's only one absorption and the stimulated emission is the same mechanism. Anyway, we will revisit that. Okay, so let's assume B12 is B21 is B. So this term becomes B times N2 minus N1. What does that mean? So that means if you have a system, you will only two levels. Your electrons is at a high level, more than the electron in the low level. That doesn't sound natural, but if it happens, that will make the material light amplified. But however, simultaneously, when the light amplifies, the electron will be moving downward. So the N2 will decrease and N1 increase. So eventually it should like equal to each other. So this if you don't have external force, this stimulated emission will only happen a very short time. That won't be a steady state. So how do you need to add extra force? Just you need to pump the water from the low level to the high level. You need to add a pump. Surely the water will flow from high to low, but if you have so many water at the ceiling, you need to add an additional pump. So we call this process pumping. So it's just like a method to pump the carriers in the low level down to the high level. So this action to keep N2 more than N1 is called the pumping. So at the beginning, very beginning, just about the method is first demonstrated. People say that it's solid state laser possible. At the beginning, people the first intuition thinking it is not, because if you want to make the N2 larger than N1 most of the time, that means your electron has more. The electron at higher energy state is more than the electron in the low energy state. So it doesn't sound this material is stable. It might melt or decompose. So people might think this might be a probably very challenging. And if we achieve that, probably the lifetime will be pretty short. Maybe only operate for 1 second, and then the laser breaks down. So not so optimistic. But it is the field fluorescent movement. It said that actually we don't need the whole solid to be inside. If we can incorporate some impurity inside the material. So, for example, for the matrix is sapphire, but the level we have some chromium inside that. Or the ruby, the chromium, the impurity is the chromium. We only need those chromium to be population inverted. Yeah. So it's like 100 million aluminum and 1 chromium. And the all chromium is excited, and that's fine because we have so many aluminum. Not excited yet, so the material should become stable. So this is the fundamental, the first idea to how to make a solid stable lace. You don't need the whole matrix to be a gammatic. You only need a small part of your cavity to be gammatic, and that is how it works. So the first step is a pump. We use a very strong lamp with the right frequency. So the electron of the solid is pumping to the high energy, but not many high percent, probably only 1% of them. Yeah, you don't need to very strong. But because the E2, the impurity level is the amount is much less than the matrix. So even only 1% leaving from the high energy state relax to the low energy state. The number of E2 is fully occupied. So if you only see the N2 and N1 between your impurity level and the matrix level, you already achieved the population inversion. You don't need to pump 50% of the material into a high energy state. So the material will be stable. So as soon as one light goes down as the spontaneous emission, the spontaneous emission will trigger another impurity with stimulated emission, and so on and so on. So light will be going back and forth. So the same idea, because it works, but people are still thinking, maybe we can design a more complex system. So from 3-level system to 4-level system, 5-level system, more level system. So the 4-level system is the idea is the same, but he only introduced the 2-level between the matrix. So you even don't need to pump the that's really hard, because for the low level it's also empty. So as long as you pump anyone to up down and to the second level here, these two will achieve population inversion, because originally there will be no any electron in the middle gap. So it makes the pumping even easier. So the most common application of these four-level laser is the NDR. And probably you will see that, or you see that in your lab, or you hear that somewhere. NDR, this kind of solid-state laser. And there's also more levels like the gas laser, helium neon laser. It is a mixture of two inner gas. One is helium and one is neon, and the composition is around 10:1. So the helium is the matrix, and the neon is the gamadium. We excite the helium by the arc, 电弧, with a pretty high voltage. So the helium is the sum of the electron at the 1s level excited to 2s, and while it colliding with another neon, the energy transferred from the helium to neon, and the neon recombine with its lower level. So you also make a stimulate population emission for neon only. And because neon have so many phenomena, so the downward transition could be 333 nanometer, could be 543 nanometer, even 3 micron. So the first demonstrated helium laser is this wavelength, 11252 micron. But people think 1 micron light is not usable. They want to a laser that is visible. I can see that. So people were very excited. So they asked, is it possible to make a helium neon laser in visible range area and finally achieve? If it happens in the 633 nanometer. It's the first application of the gas laser is the barcode. This is just like the one you see in the convenience store. But at the beginning, currently the barcode uses the laser of semiconductor laser. But before the semiconductor laser is so popular, in the beginning we use laser to shoot the barcode. So it has some real application. So why does it happen at the 633 nanometer, but not 543 nanometer? That's because the transition rate, the gap, is larger for the red light, a little bit slower and the blue light, but in the green light. But it is possible to make a green helium neon laser by changing the reflectivity of the mirror. Okay, so now the final target is, can we make a material with electrical driven material? It's called semiconductor. But the problem is the semiconductor, the energy level is continuous. It's no more a single level. What's the problem with a continuous level? If you have a continuous level, the recombination between the conduction band and the energy band, the density of state is high, much higher than the gasless or impurity level. So after you pumping it up, it has a very likely to join it back. So it will be putting it really hard. So at the beginning, people think that will be difficult to make. So we do a lot of work to constrain the available modes between the conduction band and the valence band. That's also another topic of this class. But anyway, eventually we achieve that. Anyway, what is laser? A laser is something, a gamadium. The engine is the gamadium. While it plays in the design cavity, so the light and the material can interact in a steady state manner. Steady state manner means that doesn't change with time. The interaction has the same rate over a length of time, so it is steady state. So such steady state interaction created the coherent emission. So that's the concept of laser. I think this is already pretty broad, but since the technology comes, now people think probably it doesn't need the design details. Like people think people also become aware of so many components in the random space. It's also possible to observe living material. So design material is probably not. And the second, currently we have another mechanism called polariton laser. Its interaction is light with the excitons. So if you change the interacting material to the exciton in semiconductor, you also don't need the population version. So that doesn't need to create gain. So nowadays the laser, the only important thing is you need to create a steady state coherent emission. That means your EL spectrum need to be very narrow. Yeah, I mean there's so the definition of a laser or the clear definition is also changing with time. It's not a normal clear one. So after you taking this class, you already know 90% of the laser users know more about laser than that. That's what the Professor Coulter told us in the first class of the material. But anyway, you need to remember that the semiconductor laser is an evolving field. So you have solved this knowledge from this class that will help you to keep learning the new stuff from this of this ever-growing topic. Okay, so let's take a break.